Okay, so here we are in chapter 4. We're going to talk about probability. Well, to recap, we've looked at measures of center, variation, and relative standing, and we created box plots in addition to all the things we did in chapters 1 and 2. I'm not going to lie, this chapter is all about probability and it's a lot of information. I understand that it's a lot. We need to consider how probability plays a part in our diagnostic testing as well as in hypothesis testing, which is where all of this is going. So I'm less concerned that you can calculate probabilities in the future, and I'm more concerned about you being a good consumer of diagnostic test results, which we'll look at in the discussion board. But some things must be endured, and chapter 4 is one of them. So if you do the homework and you pay close attention, the quiz is almost identical to the questions in the homework. Okay. So in section 4.1, we're going to cover probabilities as values between 1 and 0, 0 and 1, and interpret the values. We'll calculate probabilities, and we'll define the complement of an event. And I'm going to kind of gloss over some of the things that I don't feel like we need to go into in great detail. So probability plays a huge role in statistics in that we decide that something occurs by chance if the probability of that event were high, or not by chance if the probability of that event were very small. This is the idea that we're going to be using in hypothesis testing, which we'll cover in detail in chapter 8. So when you're looking at probability, you have an event, a simple event, and a sample space. An event is any collection of results or outcomes in a procedure. So looking at the picture, we have one die, and each of those die have 6 sides that range in value from 1 to 6. A simple event is any outcome that cannot be broken down into simpler components. So if I throw that die, I can only get one facing side up, right? So only one of those sides will be facing up in any given throw. The sample space consists of all the possible events, so all possibilities that cannot be broken down any further. So we have 6 possibilities. The probability that I throw, say for example, a 4 would be 1 out of 6. So for a different example, we have a pregnancy test. The procedure is the pregnancy test. The example of the event is either a positive result or a negative result, and the sample space is either pregnant or not pregnant, right? So we have 2 possibilities, one event can happen. So we have a 50-50 chance, or 0.50 probability of being pregnant or not pregnant. All right, notation and 3 common approaches to probability. P is the probability, A, B, C is the event, and the P of A, probability of A occurring, is the way that we write that, so P parentheses A. And then probability is between 0 and 1 inclusive, right? So it can be 0, it can be 1, it can be anywhere in between. We have relative frequency approximation of probability. We conduct or observe a procedure and count the times that the event A occurs. It's not theoretical, but an experimental approach. We can get a different answer each time, but as we experiment close to infinite number of times, it approaches the theoretical probability. So the probability of A is then approximated as follows. The probability of A is the number of times that A occurred over the number of times the procedure was repeated. All right, let's look. I kind of flipped around the example, so we're on example 3, page 125, skydiving. In a recent year, there were about 3 million skydiving jumps, and 21 of them resulted in deaths. What is the probability of not surviving a skydiving jump? So we have the probability of A, which is not surviving a skydiving jump, which is 21, so those are the deaths, over the number of skydiving jumps in total. So that is 0.000007. So here we have to use this approach because the probability of surviving a jump is not equal to the probability of death. All right, texting and driving. This is example 6 on page 126. In the study of United States high school drivers, it was found that 3,785 texted while driving during the previous 30 days and 4,720 did not. Based on these results, what is the probability that a randomly selected high school driver texted while driving during the previous 30 days? Okay. First we have to look at what we have, right? We're looking for the number who texted. So that's 3,785. Now, your temptation may be just to throw it over 4,720 and divide and call it a day, but it's not. It's everybody who did plus everybody who did not. So we have to do the number who texted over the number who texted plus the number who didn't text. And that we get 0.445, so 44.5% of high school students texted while driving during the last 30 days, which is kind of terrifying. Okay, classical approach to probability. This requires that each outcome is equally likely. If a procedure N has different simple events that are equally likely, and if event A can occur in S different ways, then, oops, I should have had a P of A, probability of A, the number of ways that A occurs over the number of different simple events. So S over N. I'll give you an example. Here we are on page 125. So when 3 children are born, the sample space of genders, and we typically write sample space with these curly brackets here. So we could have a girl, 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 boy, girl, boy, girl, boy, girl, girl, boy, 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 girl, boy, girl, boy, girl, boy, boy. Okay, so we have 8 different possibilities. If boys and girls are equally likely, and they are almost, then those 8 events are equally likely. So the probability of having all children of the same gender are this one, girl, 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 and boy, boy, boy. So 2 out of 8, which is 1/4, which is 1/4, 0.25. Subjective probabilities, when the probability of event A is estimated by using prior knowledge of a relevant circumstance. So the probability of getting acute appendicitis next year, we could probably find past results and use the relative frequency approach, or we can estimate based on what we know about the occurrence of appendicitis, which we know is quite small, say 1 in 1,000 or 0.001. We could be right if we are approximately knowledgeable about the subject, or we could be way off. So we don't typically do this as much. Law of large numbers. As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. The more observations, the better the estimate. Note, although probabilities can be presented as percentages, it is uncommon in research to see this. Researchers present probabilities as decimals, typically. And then we typically round probabilities to 3 decimal places, although I have seen them at 2. Okay, the complement of an event is the opposite of an event. So the probability of throwing a 1 on a die is probability of throwing a 1 is 1/6 or 0.167. Then the probability of not throwing 1 on a die, the complement is denoted with a line over it, is 5/6, which is 0.833. Or we could do it the easy way and just say the complement of P of 1 is that 1 minus the probability of 1 is the same. So we just, instead of doing the opposite, we just subtract this from 1 and get the complement's probability. All right, addition rule and multiplication rule. When we see the word or, it means addition. It's better to understand the rule than to memorize the formula. And I try to give you easy homework examples because it's really not important that you memorize this. The addition rule is used to find the probability that event A occurs or event B occurs, or that the event A and B occur. So to find probability of A or B, we add the number of ways A can occur plus the number of ways B can occur, but we add without double counting. Okay, so let's look at the drug test example on page 133. So it says, find the probability of selecting a subject who had a positive test or uses drugs. Count the number of positives in the first column and the false negatives that really are positive, and then divide by the grand total. So these are the guys that had positive tests, and then these guys actually had a positive test, but they were falsely labeled as negative. So we have 45 plus 25 plus 5 over the grand total, which is here, 555, which is 0.13. Okay, the multiplication rule. With the multiplication rule, the word and means multiplication. I'm going to have to get through a few vocabulary slides before I get to the example. So the probability that event A occurs and event B occurs, if the outcome of event A affects the probability of event B, then we must adjust the probability of B to reflect the occurrence of A. the intuitive multiplication rule. To find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B, but be sure that the probability of event B is found by assuming that event A has already occurred. Hang in there, we're getting to an example. All right, disjoint events are mutually exclusive if they can't occur at the same time. So here's an example. Event A, randomly selecting a male for a clinical trial, and event B, randomly selecting a female for a clinical trial. They're two different disjoint, you can't do them at the same time. Not disjoint events. Event A, randomly selecting someone in a statistics course, and event B, randomly selecting someone who is female. So a person could be female and in a statistics course, so those are not disjoint. All right, here's an example on page 134. Based on a journal article, the probability of randomly selecting someone who has sleepwalked is the probability of randomly selecting a sleepwalker is 0.292. If a person is randomly selected, find P not a sleepwalker. So the probability is just 1 minus that. That's what I was explaining before, which is 0.708. Independence in the multiplication rule. So two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. If A and B are not independent, then they're dependent. Just because two events are dependent does not mean that one caused the other, though. So here's an example on page 135. We have positive test results are 45 and negative results are 50, total 50. 45 and 5 with a total of 50. So if two of these subjects are randomly selected with replacement, find the probability that the first person selected had a positive test result and the second person selected had a negative test result. So this with replacement means I randomly select someone, account for them, and then put them back in the pot and randomly select again. Now there's a chance that I would select that same person again. It's possible. If I do it without replacement, I take them out and I leave them out. So let's look. The first selection, these are independent events. The probability of a positive test result is 45 out of 50. The second time, the probability of a negative test result is 5 out of 50. I'm still using 50 for both. I apply the multiplication rule with replacement. I just multiply them and I get 0.09. Okay, so that's a positive probability. The first one's positive, the second one's negative. Now, without replacement, I have to account for the fact that I took one out. So the first selection is 45 out of 50. The second selection is 5 out of 50. But when I multiply, I have to do 45 over 50 times 5 over 49. I took one out without replacement. And I get almost the same thing, 0.0918. Things to note. We must adjust the probability of the second event to reflect the outcome of the first event. But there's an exception. When drawing small samples from a population, the chance that you would draw the same item twice with replacement is very small. So we can treat these as independent when they really, really are not, to simplify greatly our calculations. So when this kind of rule of thumb is that when the sample size is no more than 5% of the population size, we can make this assumption that they are independent and sample without replacement when in fact they are not. All right. Bayes' theorem. Bayes' theorem is a way to figure out conditional probability. Conditional probability is the probability of an event happening given that it has some relation to one or more other events. For example, your probability of getting a parking space is connected to the time of day that you park, where you park, and what conventions are going on at any time. Bayes' theorem is slightly more nuanced. In a nutshell, it gives you the actual probability of an event given information about tests, and this is related to diagnostic testing. Events are different from tests. For example, there is a test for liver disease, but that is separate from the event of actually having liver disease. We could also change the word truth for event. All tests are flawed. Just because you have a positive test does not mean you actually have the disease. Many tests have a high false positive rate. Rare events tend to have higher false positive rates than more common events. Bayes' theorem takes the test results and calculates your real probability that the test has identified the event. Confusion of the inverse. So note that the probability of a positive test result, and then this little bar here, we read that as given that subject uses drugs, is not the same as the subject uses drugs given the positive test result. This happens when we incorrectly switch probability values or think that they're equal. For example, D is it's dark outside, M is that it's midnight. So the probability that it's dark, given that it's midnight, is 1. It is certain to be dark, given that it is midnight and we're not in Alaska or in Antarctica. The probability that it's midnight, given that it's dark, is close to 0 because the probability that it's exactly midnight, given that it is dark, is almost 0. If I were to randomly select any time out of the darkness, the chance that I would select midnight, right on the dot, is very, 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 very slim. All right, here's an example. Interpreting medical results. So the prevalence of cancer is 1% or 0.01. The false positive rate, so the probability of a positive cancer result given cancer not present of cancer screen, is 10% or 0.10. In a hypothetical sample of 1,000, 10 will have cancer, 990 won't. So here we have 10 with cancer, 990 with no cancer. Moving right along, a true positive rate is the probability of a positive cancer result given the presence of cancer is 80% or 0.80. So of those 10, that's 8. So the other is 2, right? So the false negatives will be 2. The other 2 will test positive but won't actually have cancer. Now, the false positive rate is the probability of positive cancer result given that cancer is not present. Of cancer screen is 10% or 0.10, so 9 of those 990 people, 10% were told they have cancer, but they really don't. Okay, so we do that math. We get 990 times 0.1 is 99 individuals who were told they have cancer, but they're really okay. And that's what we're looking at here, which leaves the remainder, 990 minus 99, which is 891 who really don't have cancer, and they go here. So, to find the probability of cancer given a positive test result, we're going to look at the first column. 8 over 99 plus 8. That's 0.0748. This is also known as sensitivity. Prior and posterior probability. It's important in Bayes' theorem, the notion of prior probability, the initial probability obtained before any more information is added, and the posterior or posterior probability, the probability value that's been revised by using additional information that's obtained later. Bayes' theorem can be used with sequential events. All right, so you'll see Bayes' theorem in practice in the sensitivity specificity PowerPoint. So we move into risk and odds. And again, I'm going to do this a little bit out of order from the textbook. We're going to compare 2 probabilities using measures of absolute risk reduction and relative risk. We're going to measure risk by calculating an odds ratio. We're going to measure the practical effectiveness of treatment by determining the number needed to treat. Okay. Relative risk or risk ratio measures how much the risk is reduced in the experimental group compared to a control group. For example, if 60% of the control group died and 30% of the treated group died, the treatment group would have a relative risk reduction of 50%, 0.5 or 50%. The rate of death in the treated group is half of that in the control group. Okay, so relative risk or risk ratio. We know that retrospective studies, data are collected from a past time period by going back in time. We know this can also be a cohort retrospective study. Prospective studies are data that are collected in future from cohorts that share some common factor. So here's our notation. We've got treatment and disease, treatment, no disease, placebo and disease, placebo, no disease. Okay, so the proportion or incidence rate of some characteristic in the treatment group is A over A plus B. A over A plus B, where the proportion or incidence rate of some characteristic in the control group is C over C plus D, so C over C plus D. A relative risk of 1 shows that the risk is the same for the treatment and control, right? It's a ratio, so when there's no, when it's equal to 1, there is the same risk for both groups. When it's much more than 1, it shows a greater risk for the treatment group. So let's do an example. All right, so we've got Salk vaccine. We have 33 kids with polio, 200,712 without polio, or tested without polio. Placebo group 115 and 2,100, 114, right, and then the totals. So the proportion of polio in the treatment group is 33 over 33 plus this large number, and we get 0.000164. And then the proportion of polio in the control group is 115 over 115 plus this number, and we get 0.000571. We put those numbers as a ratio and we calculate and we get 0.287. This is less than 1. So the interpretation is the polio rate for children given the Salk vaccine is 0.287 of the polio rate for children given the placebo. So it's less than 1, which indicates that the treatment results in a reduced risk. If we consider the reciprocal, and we put it the other way, 3.48, the control kid risk reduction is just the absolute difference in the outcome rates between the control and treatment groups. The absolute risk reduction does not involve an explicit comparison to the control group, as in the relative risk reduction, and thus does not confound the effect size with the baseline risk. However, it's a less intuitive measure to interpret. All right, so here's our sample space again, right? Absolute risk reduction is the probability of the event occurring in the treatment group minus the probability of the event occurring in the control group. So that's A over A plus B minus C over C plus D, absolute value. All right, this will always result in a positive difference between probability and treatment and control groups, and it's not always helpful. So we have to take care of an interpreting result. All right, so let's look at the polio vaccine example on page 154. So the absolute risk reduction is the probability of polio given the Salk vaccine minus the probability of polio given the placebo. So the probability of polio given the Salk vaccine is 33 over 33 plus this number minus 115 over 115 plus this number, and we get that number. So for those receiving the Salk vaccine, there is an absolute risk reduction of 0.000407 when given the vaccine as opposed to the placebo. In other words, there are 0.0407% fewer events of polio for those receiving the vaccine, but that's not very intuitive. So we look at the number needed to treat. The number needed to treat is the number of subjects that must be treated in order to prevent one event, such as the disease or adverse reaction. It is calculated by dividing 1 by the absolute risk reduction. So we use this round off rule. If you get a fraction, you round up to the next larger whole number. Okay, for example, the same exact problem, we get 1 over this probability, and we get 2,458, because we're going to round this up to a whole person. Therefore, we would need to vaccinate 2,458 children with the Salk vaccine instead of the placebo to prevent one of the children from getting polio. Given the seriousness of polio, the Salk vaccine was found to be effective and important. Odds. Probabilities are expressed in values between 0 and 1. However, likelihood is often expressed in odds, such as 50 to 1, or written out like this, 50 to 1. Actual odds against an event occurring are the ratio of the probability of not A over the probability of A, usually expressed in the form A to B or written out, where A and B are integers. The actual odds in favor is the reciprocal, so the probability of A over the probability of not A. If the odds against are AB, then the odds in favor are B to A. Here's an example. So rehospitalization and discharge. For those babies discharged early, find the probability of being rehospitalized within a week. And then for those babies discharged early, find the odds in favor of being rehospitalized early. All right, so we have early discharge, less than 30 hours, late discharge, greater than 30 hours, rehospitalization within a week, not rehospitalized within a week, and then the totals. So for those babies discharged early, find the probability of being rehospitalized within a week. So the probability of being rehospitalized is 457 out of the total, which is 1/8. So 457 over 457 plus this, which is just this number I gave it to you. So for those babies discharged early, find the odds in favor of being rehospitalized early. So the probability of being rehospitalized within a week was 1.8. Well, I'm sorry, 1/8. Then the probability of not being rehospitalized is 1 to 7, or 7/8. Odds ratio. In a retrospective or prospective study, the odds ratio, denoted OR, or relative odds, is a measure of risk found by evaluating the ratio of the odds in favor to the treatment, or exposed to the risk factor, to the odds in favor of the control group. So we have the odds in favor of a treatment over odds in favor of the control. Same contingency table. Odds ratio is AD over CB. So you can just cross multiply. A times D over C times B. So looking at the table, the odds ratio for rehospitalization is AD 457 times 2,860 over 260 times 3199, and we get 1.5, or 1.6 essentially. Results indicate that the odds in favor of rehospitalization are 1.571 times higher for babies who were discharged early when compared to those who were discharged late. Why not use risk ratio in retrospective studies? Risk ratios make sense if probabilities are good estimates of the actual incidence rates, as in a prospective study. However, researchers could choose disease cases that are different from real incidence rates. For this reason, odds ratios are used for retrospective studies, and risk ratio is used for prospective studies only. So, relative risk, prospective studies. Odds ratios can be used for both. Watch the video, it explains it very, very well.